Hello everybody. In this short presentation I'd like to just give you a flavour of our experiences in developing the global pneumococcal sequencing project. And I'm speaking here on behalf of my co-authors listed here. So to begin with, let's look at the motivation. So the pathogen itself, Streptococcus pneumoniae, is a major cause of disease globally. In 2018 there was a report that estimated that there had been 3.7 million episodes of severe pneumococcal disease, including over 300,000 deaths, and that's just in children under the age of 5 and just in the year 2015. And that is despite a big reduction in the numbers of deaths that's happened since vaccines have been introduced widely since the year 2000. So the vaccines themselves target the polysaccharide coat on the outside of the bacterial cell, shown in this picture here. And Streptococcus pneumoniae has at least 100 different types of this polysaccharide coat, which are referred to as serotypes. And the vaccines at the moment target up to 13 different serotypes. So you can already see that there's potential for the species to evade that vaccine. So back when next generation sequencing came online around 2009, we started to apply that technology to looking at pneumococcal genomics, pneumococcal evolution, and try and think about this vaccine evasion problem. And we could show just here by looking at one strain that recombination serves to relatively frequently change the locus that encodes the polysaccharide capsule, so that this strain, for example, can change to multiple different serotypes, some of which are inside the vaccine and some of which are outside the vaccine. And then the vaccine simply serves to select those which are not covered by the vaccine, and those can expand in the population. So the panel on the right here is showing what we can see if we look species wide, and what we can use genomics for is to show the change in prevalence of different strains through the introduction of vaccine, and then show how the population as a whole is responding to the vaccine. So some strains which are outside of the vaccine will just grow anyway. And then other strains where there's a mixture of serotypes, there'll be this selection process for capsule switch events. Okay, and that was work done by Nick Croucher during his PhD at Sanger and then postdoc at Harvard. And really set us in a good place to start to think about applying genomics to surveillance of this pathogen. So in discussion with Keith and Leslie, and guys at the Gates Foundation, we were able to put together this idea for a project which the Gates Foundation funded. And it was based on the calculation that, it was a back of the envelope calculation that 20,000 genomes would be possible with a reasonable amount of money, and that would give us a decent coverage of the globe, looking at variation before and after the introduction of vaccine. Samples, to ensure that we would have access to good quality samples, initially we engaged with these three groups, these founding partners based in the Gambia, Malawi and South Africa. And these were groups who were very experienced in working with the pneumococcus and well-resourced to be able to isolate the samples that would be necessary. We also accessed 2,000 samples from the US national surveillance system, US being the place where the vaccine had been introduced first. And at CDC there was also available the global strain bank of 3,000 samples, which gave us a reasonably good sampling of the globe. And then that left us with 6,000 samples to fill in the gaps and try and engage with countries to help us with this aim of capturing a global pneumococcal genomic diversity sample pre and post vaccine. So important to point out that in this phase of the project, all of the sequencing was done at Sanger. So the DNA was sent directly to Sanger from the project partners, or they sent strains to CDC where the DNA was extracted. But all sequencing was done at Sanger, And then the majority of the analysis, at least initially, was done at Sanger, and then as time has gone on, more and more partners have got involved in the analysis process. So you can see, I'm just pointing to the map on the right here. This is where our partners are now, and so you can see that we did make good progress in engaging with people from lots of different countries around the world. And the focus was really on the low and middle income countries where Gates and Gavi were supporting the rollout of pneumococcal vaccine. And this is just a single slide, but it actually represents an enormous amount of work and a large proportion of the work that we had to do and have had to do and will continue to do in the project. And it's around engaging with people and engaging with partners to make sure that we can deliver what we want to deliver. And a lot of this is pretty non-scientific, but it's absolutely essential. So we had our founding partners, which was a real bonus to begin with. And then through those partners and through our own connections, we were able to recruit other collaborators. We did literature surveys to see if there were people that we didn't already know about who would be potentially interested, and then we also advertised at conferences. And when we identified potential partners, we put a lot of effort into learning about their interests, their priorities, their preferences, and what they would potentially be capable of doing and interested in doing to contribute to the project. What were they interested in getting back out of the project? We had to spend a lot of time carefully talking to partners about the potential availability of samples and ensuring that there was good metadata associated with those samples. And just to note, we sequence any samples without already having the metadata in hand. For each country, we needed to understand their vaccine rollout potential, and then for partners to understand whether they would prefer to supply DNA, do DNA extractions themselves and send the DNA, or simply send strains. And initially that was to CDC. And in either case, we want to do a phase of QC to check that everything that went onto the sequencing machine was going to produce good quality data. And then there's also other non-scientific stuff that's really important to reassure people that this is all worthwhile for them. So data sharing is an obvious one. And fortunately, we were supported by the Wellcome and Gates Foundation in having a very open data policy. We produced a collaboration and publication guidelines document, which was really to reassure partners that there would be fair play. It's not a legally binding document, but it was just to reassure people that we were coming at it from a fair play point of view with the research. Related to that, we really encouraged partners to propose sub-studies that would be done within the wider GPS database, and often that was really successful in linking together partners across the project where people had shared interests, and we managed to put together lots of really interesting collaborations on that basis. There's obviously a bunch of legal paperwork that's necessary in these kinds of situations, so MTAs, RCAs, Nagoya agreements, and financial transfer, which I won't go into right now, but as I say, these are all really essential. And then there's the logistics of shipping consumables around the world and samples around the world. So as I say, a single slide, but an enormous amount of work and really important to the success of the project. So in terms of outputs, and this is just for the GPS 1 phase, we're now moving into GPS 2. For GPS 1, obviously the genomic data itself is fundamental, and here in this graph you can see that we hit our target of 20,000 midway through 2017, and then have continued to generate more data since then. We also have created through the term of the project, we've created various web resources. So I haven't got time to describe them all in detail, but if you go to the website there, you can find them there. There's interactive databases, particularly for the metadata, so you can explore the metadata. Data downloads, which was really important for all of the partners. Analysis tools, which is really something that's beginning to grow. And we're working with various collaborators on various different analysis tools, and visualizations of analyses that we've done, so presenting those in an interactive form on the web. In terms of papers, we didn't really get cracking with papers until we had a decent amount of data, but then there's been 21 papers out so far, and then another 15 that are in preparation. And it's really pleasing to see these large numbers of abstracts at conferences. And a lot of this is partners working on data for their own particular country and wanting to present those to the wider world. Two really important outputs, I would say, have been the fact that once we have this global data set, we're then in a position to be able to try to define the strain structure of the species with that rich global data set. And this is work that John Lees did, developing an algorithm called PopPunk, which has the advantage of using all of the sequence from all of the genomes in defining those relationships between strains, and that's really important. And then finally, kind of the jewel in the crown is this the fact that we've managed to produce information that's useful in vaccine design. So in the endeavour to prevent disease going forwards. And this is just to summarise an example of where that has been specifically useful. So the database generally is useful for surveillance, and surveillance is useful for vaccine strategy. But here's a particular example where, using the GPS data, we were able to characterise serotype 24F as being, so one specific serotype as being a significant non-vaccine type that was emerging post-vaccine introduction. And then we're able to show that within all of the serotype 24Fs, one strain known as GPSC10 is the main contributor to the rise in serotype 24F. And that strain is unusually virulent, so we can show that by odds ratio for disease across the data set. We could also show that, and this wasn't already known, but we could show that strain is very diverse in terms of the serotypes that it's able to express. It's able to express 17 different serotypes. Only 6 of those are covered by the current vaccine. So 24F, this major emerging serotype, has now been included in the third generation vaccine, and surveillance can now be alert to the fact that GPSC10 may be continue to be a risk for the emergence of non-vaccine type disease in the future. So I haven't got any more time to describe this, but I would encourage you to go and seek out Steph Lowe's poster, which describes her analysis on this. So we're now, as I say, moving into the next phase, which we sometimes refer to as GPS2, and this is the title from the proposal, which was establishing decentralised global genomic surveillance for the pneumococcus. So as I showed before, in the first phase, all of the sequencing was done at Sanger, but now we want to really push that out so that partners in their home countries can generate and analyse the data. So we have 2 main priorities in this next phase. One is to fill the data gaps, which I'll show you in a moment, and then the other is this helping to build capacity for local sequencing and analysis. So in terms of data gaps, going back to the global burden study that was published in 2018, they showed there that 50% of all pneumococcal deaths in 2015 occurred in just 4 countries: India, Nigeria, DRC, and Pakistan. And then when we went to look in our GPS1 database, we found that those countries were only represented by 5.6% of the data. So I'm pleased to say that we're making good progress in addressing that data gap by engaging with really fantastic, enthusiastic people in all 4 of those countries. And I'm confident that in this next phase we're gonna really do good work to fill that data gap and make the database more relevant to the burden of disease. So I'm sure at this conference there'll be lots of talk about local sequencing setup. It's really important. It's gathering momentum, and this slide is a very high-level summary of some of the challenges. So at the beginning, you can obviously, in some countries, in high-burden countries, there may be some serious challenges in terms of just electrical power, internet, and just general setup of labs themselves. there's limits to what we can do about that. The next major thing that I've pointed out here is local expertise. So expertise to do the sequencing and to do the analysis. That I think there's really obvious things that we can do about that in terms of training. Supply of sequencing hardware is definitely improving. The companies are doing a much better job of selling their wares to the high burden, low income countries. However, supply of consumables remains a major challenge, and costs can be very variable around different locations in the world. But I think there's going to be progress on that in the not too distant future. Actually, samples themselves can be a major challenge, and that is a major challenge for the pneumococcus, and I'll come back onto that in a moment. And then I've just put here at the bottom the COVID effect. So I think COVID has had both negative and positive effects for the GPS project. So negative in that all of our partners are directly interested and involved in respiratory disease. So a lot of their attention has been diverted towards COVID. But I hope that that's just going to be a short-term effect, and the long-term effect will be more of a positive one, where I think COVID has highlighted and demonstrated that genomic surveillance of pathogens can be very valuable, and that means that there's been a lot of investment in that direction. So I hope we can benefit across all of the different pathogens. In terms of training, this slide is to just summarize some of our activities through GPS and JUNO. So JUNO is a partner project that we have, again funded by the Gates Foundation, and again to look at genomic surveillance of a pathogen where there is a vaccine. In the case of Group B strep for JUNO, the vaccines haven't actually been rolled out yet, so it's interesting to get there before the vaccine. In the solid boxes, we have things that Christine is developing directly within the GPS and JUNO project. So that's a mixture of online training resources, face-to-face training, support through webinars and direct messaging. And then there's also a link with the Train the Trainer program, which is led by Wellcome Connecting Sciences. And one of the things I'd like to point out here is that Christine has done a fantastic job in generating materials and resources for training, but also integrating with other organisations who are doing overlapping things and similar things, and just really creating synergy between these organisations. There's a wide acknowledgement that genomic surveillance is useful, and there's lots of synergies to be had. So going back to Nick Croucher's initial work, I think genomic surveillance has got foundations in basic research that's been done at Sanger and other places. And that basic research continues and will continue to benefit genomic surveillance, I think. So, for example, Jerry Tonkin-Hill has just completed his PhD, where he was looking at deep sequencing data to really look at diversity within host and transmission events. But what he's revealed is that deep sequencing data can be really good at detecting strains that are rare in Carriage. And that really helps us to think about whether Carriage surveillance can be useful in places where disease surveillance is difficult. So in many places, isolating pneumococcus from cases of disease is really challenging. And that can be either because of limited microbiology resources, or because many patients have got prior antibiotic use, so you're just not going to isolate a live organism. So sampling from Carriage as a surveillance exercise can be useful, but that's only if we can confidently extrapolate a disease population from the Carriage population, and that's research that we're trying to do now. Sophie Bellman is a new PhD student, and she's trying to use genomic data to look at migration of strains. So it's well acknowledged that strains do move around the world, but until now, most of that description has been very qualitative in terms of how strains are moving. And what Sophie's trying to do is use the genomic data and other metadata to really quantify how strains are moving, and then that will be useful in forecasting risk of emerging strains in the future. So there's an enormous amount of people, an enormous number of people who've been involved in GPS so far, and I'm sure this number is going to grow. I'm not going to call out any one individual at this point, but I just want to thank everybody for their generous contributions so far, and I'll leave it there. Thank you.